Good evening everyone, good evening. I welcome you all again to your Vedantu Enlite channel. I hope you all are doing great, having a good time. So people, quickly let me know in the chats if I'm perfectly audible and visible to everyone. Yes. Let me know quickly in the chats, my dear people, if I'm perfectly audible and visible to everyone. Yeah. Let me quickly know in the chats. Hello Anabia, hi Hariharan, hello Tariq, hi Ashwarya. Welcome back everyone, welcome back. Welcome back. Just give me a second, we'll be starting, right? Just give me a second. Perfect guys, so as you all must be knowing, tonight we are going to have a session on the chapter Chemical Kinetics, right? Well, in this particular chapter, my dear people, what all things I'll be covering all the problem patterns which can be asked from this particular chapter in your upcoming NEET examination, right? And whatever concepts are involved in every question, I'll be discussing the concepts first, then we'll be solving the questions, right? So concepts and the questions. Perfect. So before starting tonight's session, the ones who have just joined in, the ones who are new to the channel, let me quickly introduce myself. So people, my name is Wassim and I'm your chemistry master teacher right here on this Vedantu Enlite channel, right? The ones who have not liked the video yet, please do like the video, share the video with friends, do subscribe to the channel, and do not forget to hit the bell icon so that you get the notification of every single session which we take live on this Vedantu Enlite channel, right? So do like the video, share the video with friends, and do subscribe to this particular channel as well, okay? Perfect. So let me know quickly in the chats, my dear people, if all of you are super duper excited about this particular session. Nana, this chapter will take 2 sessions. This chapter will take 2 sessions to finish, right? Let me quickly know in the chats, my dear people, if all of you are super duper excited about this particular session as well, yeah? Perfect guys, so let's get going then, let's get started, and let's first of all talk about the rate of the reaction, right? This is the first topic, my dear people, which I'm going to talk about right now. See, first thing, for example, I'm writing a balanced chemical equation as N1A plus N2B. It gives, for example, N3C plus N4D. Let's say this is the balanced chemical equation which we have, in which the stoichiometric coefficients of reactants and products are N1, N2, N3, N4 respectively, right? Now over here I'll be writing few terminologies. The first terminology which we are going to write over here, that is the rate of disappearance. Rate of disappearance of A. How do we write it mathematically exactly? The rate of disappearance of A. We start with the minus sign, then we'll be writing change in the concentration of A divided by dt. This is how you write rate of disappearance of A. Similarly, my dear people, rate of disappearance of B, how you're going to write it, you'll be starting with the minus sign. It's going to be change in the concentration of B divided by dt. Similarly, there's a term called as rate of appearance. Rate of appearance of C. Rate of appearance of C, I'll be starting with the plus sign. It's going to be change in the concentration of C divided by dt. And then I'll be writing rate of appearance of D. It's going to be plus times change in the concentration of D divided by dt. So first of all, I would want you guys to know how do we write the rate of disappearance and how do we write the rate of appearance. Perfect. Now people, if I talk about the rate of the reaction, how do we write the rate of reaction in the form of differential equation? Rate of reaction can be calculated either with respect to A or with respect to B or with respect to C or with respect to D. If I write the rate of reaction with respect to A, I'll be starting with minus sign, 1 divided by stoichiometric coefficient of A, that's N1, change in the concentration of A divided by dt. So this term is going to give you the rate of the reaction. Similarly, my dear people, you can write it with respect to B as well, starting with minus sign, 1 by stoichiometric coefficient N2, change in the concentration of B divided by dt, right? Similarly, I can write it in terms of C as well. Since C is the product, I'll be starting with the plus sign. 1 divided by stoichiometric coefficient N3. It's going to be change in the concentration of C divided by dt. Then I'll be writing plus 1 divided by N4, change in the concentration of D divided by dt. So people, this is how you write the differential form of rate with respect to any of the reactant or any of the product, right? Now, first of all, let's exactly get to know how do we use this particular equation and how do we use these sort of terminologies in the questions, right? So let me directly get started with the first question, which is on your screen. See guys, a very simple and basic question this is. If the concentration of H2O2 changes from 0.5 molar to 0.05 molar in 15 seconds, then calculate the rate of reaction. Well people, this is a particular reaction that's given to me. Let me write the differential rate for it. It's going to be equal. With respect to H2O2, you'll be writing minus times change in the concentration of H2O2, change in the concentration of H2O2 divided by time interval, right? Similarly, you can write the rate with respect to H2O as well. You're going to write it as plus, since the stoichiometric coefficient is 1, plus delta change in the concentration of H2O divided by time interval delta t. You can write it with respect to O2 as well. It's going to be plus 1 by stoichiometric coefficient. Stoichiometric coefficient is 1 by 2, so the 2 comes up. Change in the concentration of O2 divided by delta t, time interval, right? So first of all, this is the equation which I wrote over here, right? Or people, just to make it a little more simplified, let me write it in the form of D, right? Rate of reaction is equal to minus times D of H2O2 divided by dt, because this is the equation which I gave you a few minutes back, right? Similarly, in terms of H2O, it's going to be D of H2O divided by dt. Similarly, in terms of water, it's going to be plus 1 by stoichiometric coefficient, so 2 comes up, D of O2 divided by dt. Perfect. Now, as per the question, have a look exactly what all things we are going to see. First thing, calculate the rate of reaction. Well, people, I can calculate rate of reaction by solving any of these terminologies over here, right? So I can write rate of the reaction is equal to minus times change in the concentration of H2O2, which is going to be exactly final concentration of H2O2, which is 0.05, minus initial concentration of H2O2 divided by time interval is given to you as 15 seconds, right? You can solve this expression, get the value of rate of the reaction in moles, liter inverse, second inverse, number 1, right? Number 2, my dear people, calculate the rate of appearance of O2. Once you calculate the rate of reaction, now it is the time to calculate rate of appearance of O2, right? Now people, let me take this term and this term out of this particular equation, right? So what I'll be writing? I'll be writing minus D of H2O2 divided by dt is equaled plus times 2 D of O2 divided by dt. So from this particular equation, I can write D of O2 divided by dt as minus 1 divided by 2. It's going to be change in the concentration of H2O2 divided by dt. This is how you're going to write it. Simple. That's all, right? So it's going to be minus 1 by 2. Change in the concentration of H2O2. It's going to be final concentration of H2O2 0.05 minus initial concentration of H2O2, that is 0.5, divided by time interval is given to us as 15 seconds. Just solve it, get the answer in moles, later inverse, second inverse, right? So this is something which we call as rate of appearance of O2, which I was supposed to calculate as far as the second part of the question was concerned. Let me know, people, in the chats if it's clear to everyone fast. Fast, people. Let me know quickly in the chats, my dear people. Yes, clear to everyone? Perfect. Yes, Russell, I'm going to teach in Hindi as well, right? I'm going to teach in Hindi as well. Yes. Just wait for it. All right, look at this particular question, guys. This is something which you can solve on your own now. I'm sure about it. The question says, if the rate of appearance of O2. How do I write the rate of appearance of O2? I'll start with the plus sign. D of O2 divided by dt. This is something which we call as rate of appearance of O2, right? It's given to us as 0.5 moles liter inverse second inverse. So this is something which we call as rate of appearance of O2, right? Now what do I calculate basically? What do I need to calculate? I need to calculate rate of disappearance of N2O5. How do I write rate of disappearance of N2O5? I'll start with minus sign, change in the concentration of N2O5 divided by dt. This is what we call as rate of disappearance of N2O5, which I'm supposed to calculate, right? Now, first thing, my dear people, for this particular reaction, let me write the differential form of rate. I'll write rate of reaction is equal to, I'll start with the minus sign, 1 divided by stoichiometric coefficient of N2O5 is 2, change in the concentration of N2O5 divided by dt, which you can write in terms of N2O4 as well, since N2O4 is the product, so start with the plus sign, 1 by stoichiometric coefficient, that's 2, change in the concentration of N2O4 divided by dt, right? You can write it in terms of O2 as well, plus d of O2 divided by dt, right? What do I need to calculate? I need to calculate the rate of disappearance of N2O5, right? So let me just take this term out of this particular equation and this term. Let me just equate these two terms, right? Let me just equate these two terms. Perfect. I'll be writing minus d of N2O5 divided by dt is equal. I'll take this 2 over here. It's going to be plus 2 times d of O2 divided by dt. That's all, right? So it's 2 times. d of O2 divided by dt is something which we call as rate of appearance of O2. That's given to me as per the question. That is 0.5. So the value comes out to be exactly 1 mole liter inverse second inverse. This is something which we call as rate of disappearance of N2O5, which I was supposed to calculate, right? Let me quickly know in the charts if it's clear to everyone fast. Exactly. Perfect, guys. I'm sure you can solve these sort of questions from now onwards easily, right? Look at this particular question, my dear people. See what the question exactly says. Have a look. For the following reaction, a curve for concentration versus time is given. Since the reaction is given, and for this particular reaction, we are given with a curve, right? Well, people, as you can see, as the time passes on, the concentration keeps on decreasing, and you know, concentration of reactant decreases with time, right? So this is basically the curve which is valid for the reactant. Perfect. And what is my reactant over here? That's NH3. So the curve is valid for NH3. The curve is valid for NH3, right? Now what do I need to calculate? I need to calculate the rate of reaction in the interval 5 to 15 seconds. In this particular time interval, I need to calculate rate of reaction. So when the time is 5 seconds, the concentration of the reactant, which I represent with C1, is 0.6 moles per liter. When time T2 is 15 seconds, at that time concentration of reactant left is 0.2 moles per liter per second, right? I need to calculate the rate during this time interval. So I'll be writing rate of reaction is equal, right? I'll be writing it with respect to NH3. I'll start with minus sign, 1 divided by 2, right? It's going to be change in the concentration of NH3 divided by time interval, that's delta T, right? So it's going to be minus 1 by 2. What is the change in the concentration of NH3, my dear people? It's going to be final concentration of NH3 minus initial. So it comes out to be 0.2 minus 0.6 divided by time interval 5 to 15 seconds. That means the time interval is 10 seconds, right? Now just solve this part, get the answer in moles liter inverse second inverse, right? This is something which you were supposed to calculate as far as the question was concerned. That's it, right? Perfect. Let me know, my dear people, in the chats if it is clear to everyone so that I can move on. One more type of question which you have on your screen, my dear people, a very simple and basic question. Well, we are given with a reaction. We need to calculate, and some data is given to us. Have a look. We need to get the relation between K1, K2 and K3. Right? We need to get the relation between K1, K2 and K3. First thing, I'll be writing rate of this particular reaction. With respect to N2O5, I'll start with minus sign. Change in the concentration of N2O5 divided by dt. Similarly, with respect to NO2, I'll start with plus sign, 1 divided by stoichiometric coefficient, change in the concentration of NO2 divided by dt, which you can write in terms of O2 as well. You'll start with plus sign, 1 by stoichiometric coefficient. So 1 by 2 comes out to be 2, change in the concentration of O2 divided by dt, right? Now see what all parameters are given to us, my dear people. Minus times d of N2O5 divided by dt, this term is given to me as K1 multiplied by concentration of N2O5 is equal to plus 1 by 2. D of NO2 divided by dt is given to me as K2 multiplied by concentration of N2O5, right? Similarly, I've got 2 over here. D of O2 divided by dt is given to me as K3 multiplied by concentration of N2O5, right? Perfect. So this N2O5 concentration, this one and this one gets cancelled out. So the final expression you'll be getting as K1 is equal to K2 divided by 2, which is equal to 2 times K3. Now, if I'll multiply throughout with 2, this becomes 2 times K1 is equal to K2 is equal to 4 times K3. So this is, people, the relation between K1, K2 and K3 which I was supposed to calculate. Perfect? Clear to everyone? Fast? This is how you are going to approach to this sort of equation, right? And do remember the approach from now onwards. Clear to everyone? Venkat, you can watch the video at 0.5x speed, bro, if speed is the problem, because it's a one shot, right? One shot means the session is going to be crisp, to the point, with some nice speed, right? Let me know quickly in the chats if it is clear to everyone. Fast? Perfect, guys. Let's move on and let's talk about the relation between different rate constants, right? Let's get to know about the relation between different rate constants. People, have a look. Let me write one simple relation over here and do remember it from now onwards. Rate constant of disappearance or appearance of a reactant or product is always equal to rate constant of the reaction multiplied by stoichiometric coefficient of the reactant or product. What is meant by that? Say, if I write K1, K1 is something which we call as rate constant of disappearance of A. It's going to be equal to rate constant for the reaction multiplied by stoichiometric coefficient of A. Similarly, if I write K2, K2 stands for rate constant of disappearance of B. It's going to be rate constant for the reaction multiplied by stoichiometric coefficient of B, that's N2, right? Similarly, my dear people, if I write K3, K3 is something which I call as rate constant of appearance of C, which is going to be rate constant for the reaction multiplied by stoichiometric coefficient of C. And then if you want to write rate constant for the appearance of D, it's going to be equal to rate constant for the reaction multiplied by stoichiometric coefficient of D, which is N4. Do remember this relation, which is between the rate constants, different rate constants in a particular reaction. Now, where do I use this? For example, you have got a question like this, right? This is one question which I'm starting with, right? I'm going to use the concept in this particular question. Perfect, people? Have a look exactly what I'm going to do. First thing, the reaction is given to me as 2 times A plus 3 times B gives C. I need to get the value, I need to get the relation between K1, K2 and K3. Perfect. Now, first thing, my dear people, K1 is nothing. K1 is equal to rate constant for the reaction multiplied by stoichiometric coefficient of A, that's 2. Similarly, K2 is going to be equal to rate constant for the reaction multiplied by stoichiometric coefficient of B, that's 3. And similarly, K3 is going to be equal to simple rate constant of the reaction multiplied by stoichiometric coefficient of C, that is 1, right? Now, people, from this particular equation, you can write rate constant for the reaction, which will be equal to K1 divided by 2. Similarly, right here, rate constant for the reaction is going to be equal to K2 divided by 3, right? And over here, rate constant for the reaction is equal to K3. Now, if you look at these three equations, my dear people, you can clearly say K1 divided by 2 is equal to K2 divided by 3, which is equal to K3, right? Now, if I take the LCM of the denominators, that will come out to be 6. If I multiply throughout with 6, it becomes 3 times K1 is equal to 2 times K2 is equal to 6 times K3. So this is going to be the relation between K1, K2 and K3, which you were supposed to calculate as far as the question was concerned, right? Let me know quickly in the chats if again this is clear to everyone. Fast. Let me know, people. Let me know in the chats. Perfect. All right, guys. So let's have a look and let's try to see a few more important things, right? Question on your screen. I would want you guys to give it a try and let me know its answer in the chats. It's a very simple one. The question says, for a chemical reaction A gives B, it is found that the rate doubles when the concentration of A is increased 4 times. Find the order of the reaction. First of all, the reaction that's given to me, that is, for example, A gives B. Its rate constant is K, right? I'm assuming order of this particular reaction is equal to N. I'm assuming order of this particular reaction is equal to N, right? Simple thing. First thing, I'll be writing the rate law, my dear people. Whenever you need to calculate order of some reaction, you first of all write the rate law, right? So as per the rate law is concerned, rate of the reaction is equal to rate constant multiplied by concentration of A raised power N. Let me call this as reaction number 1, equation number 1, sorry, right? Now, as per the equation, my dear people, when the concentration of A is made 4 times, right, the rate doubles. So initially the rate was R, now it becomes 2R, right? When the concentration of A is made 4 times. Let me call this as equation number 2. So if I divide both the equations, it becomes 2 is equal to 4 raised power n. This is something which you get when you divide these two equations, right? So from here, you can clearly say n value should be equal to 1 by 2. And what was n? N was the order of the reaction. So you got the order of reaction exactly as 1 by 2. That's all. 4 raised power n is equal to 2. So the power of n has to be 1 by 2. That's it, right? Simple. I'm sure you can solve these sort of questions easily from now onwards. Just a second, guys. What happened to this? Okay. See, guys, a rate law is given to us. The reaction is also given to us. We are supposed to calculate the order of reaction, right? And then the conditions are given. If the concentration of Br2 is kept very high, and then in the second equation, if the concentration of Br2 is kept very less. So let's try to solve the first part of the equation, right? If the concentration of Br2 is kept very high, so at that point of time, instead of Br2 plus K2 multiplied by concentration of HBr, I'll be only writing concentration of Br2. This is the condition which is given to us. If the concentration of Br2 is kept very high, so instead of this whole term, I'll be only writing Br2. That's it, right? Now we will have a look. Now I'll be writing the rate law again. It's going to be equal to K1 multiplied by concentration of H2 raised power 1 multiplied by concentration of Br2 raised power 1 by 2, and in the denominator you'll be only writing Br2. That Br2 comes up, right? It becomes minus 1 over here, right? Now people, what is the power right here? It's 1. Just a second, my dear people. This is 1 by 2 and Br2 comes up, so the power becomes minus 1, right? So have a look exactly. So what is going to be the order of reaction? See, guys, the power right here is 1, the power right here is minus 1. So order of reaction with respect to H2 is 1. Order of reaction with respect to Br2 is minus 1, right? So what is going to be the overall order of the reaction? This plus this. That means overall order of the reaction is going to be 0. Overall order of the reaction is going to be 0. So first part of the equation is done. Look at the second part of the equation, my dear people. If the concentration of Br2 is kept very less. Well, if the concentration of Br2 is kept very less, so instead of K2 HBr plus Br2, I'll be only writing K2 multiplied by HBr. So then I'll be writing a rate law. It becomes K1 multiplied by concentration of H2 raised power 1, concentration of Br2 raised to the power 1 by 2, and in the denominator it is K2, right? In the denominator it's K2, perfect. HBr comes up, so it becomes HBr raised power minus 1, right? That's all. Now people, this is a constant, division of two constants becomes one more constant, which I represent with K dash, right? This is concentration of H2 raised power 1, concentration of Br2 raised power 1 by 2, and concentration of HBr raised power 1, right? So look at the powers, my dear people. This is 1, this is 1 by 2, this is 1, right? So what is going to be the overall order of the reaction? It's going to be 1 plus 1 by 2 plus 1, right? So it comes out to be 5 by 2. That's it. Perfect, my dear people. Simple and basic, right? Perfect. I think I missed something, guys. Just a second. It's minus 1 here. It's not plus 1, right? It's minus 1 here. So it's minus 1. So order of the reaction is not going to be 5 by 2. It's going to be 1 by 2. Right? Now it's perfect. I'm sure it's done. So let me quickly move on to one more then. This is one more type of question which is asked in your examination, my dear people. You need to calculate the order of reaction with the help of certain experiments, right? Let's exactly see how these sort of questions are to be solved. This is the reaction that's given to me. I'll be first of all writing its rate law, which is going to be rate constant multiplied by concentration of NO raised power X, concentration of H2 raised to the power Y, right? So I need to calculate the value of X first, then I'll be calculating the value of Y, then I'll be taking the sum of X and Y. That gives me the overall order of the reaction. That's something which you already must be familiar with, right? Now we will have a look. In the first two experiments, the concentration of H2 is kept same, right? Concentration of H2 is kept same. and concentration of NO is increased 3 times. And what is happening to the rate of reaction? Rate of reaction is also increasing 3 times. So on increasing the concentration of NO 3 times, rate of reaction is also increasing 3 times. That means the power has to be 1. That means this power has to be 1, right? Because it's mentioned in the question. I just looked at the experiments. On increasing the concentration of NO 3 times, the rate is also becoming 3 times, right? So concentration of, power of NO has to be 1. Perfect. Now, if you look at the second experiment and the third experiment, I'm increasing the concentration of H2 4 times. What is happening to the rate? Rate is also increasing 4 times. On increasing the concentration of H2 4 times, rate is also becoming 4 times. That is only possible if the Y value is also 1. So X is 1, Y is 1. So overall order of the reaction is going to be 1 plus 1. That is 2. That's it. Right, people? Let me know quickly in the chat if it is clear to everyone. Fast. Exactly, my dear people. Exactly. Let's have a look on a few more questions. Okay. Now let's talk about something called as zero order reactions, right? Let's have a look what kind of questions are asked from these zero order reactions. See guys. First of all, let's say this is the reaction which I have A gives B. I'm assuming its rate constant is K. I'm assuming the order of the reaction is equal to 0, right? This is something which I'm assuming right now, okay? Now, first of all, at time t is equal to 0, initially, let's assume the concentration of reactant is A0. This is going to be 0. At some time t, the concentration of reactant left is represented by AT, and the concentration of product formed is represented by BT, right? Be careful with the terminologies. This is the concentration of reactant initially. This is the concentration of reactant left at time t. This is the concentration of product formed at time t, right? Now, as per the integrated rate equation for the zero order reaction is concerned, it is something like this. AT is equal to A0 minus KT. You call this equation as the integrated rate equation for the zero order kinetics, for the zero order reactions. As simple as that. AT is equal to A0 minus KT, right? Perfect. Now, we will one more equation. I'm sure you all must be familiar with that. That's half-life. How do we calculate half-life of a zero order reaction? It's simply equal to A0 divided by 2K. This is the relation to calculate half-life, time taken to complete 50% of the reaction, right? If I ask you, how do we calculate completion time, T 100%, how much time it takes for the reaction to complete 100% of it? It's equal to A0 divided by K. This is one more thing which I would want you guys to remember. Now, people, if you look at this T half expression and T 100% equation, if you compare these two equations, you can clearly get T 100% is equal to 2 times the half-life of the reaction. That means a zero order reaction is 100% completed in 2 half-lives. A zero order reaction is 100% completed in 2 half-lives. This one more equation which I would want you guys to remember. Then comes one more parameter, that's alpha. Alpha means degree of dissociation. How do I calculate degree of dissociation, my dear people? Number of moles of reactants dissociated into products divided by initial moles of reactants. So initially I had some A0 moles of reactant. At time t, there are 80 moles of reactant left. So how many moles of reactant got converted into the product? It is A0 minus 80. These many moles of reactants got converted into products, or I can say these many moles of reactants got dissociated, right? Divided by Ni, which means the initial moles of reactant, that is A0. So alpha from here is simply going to be equal to A0 minus 80 is nothing, that is A0 minus KT. Perfect, divided by A0. So from this particular equation, alpha is going to come as KT divided by A0, right? This is one more expression which is only and only valid for zero order reactions. Perfect, people. These are some of the important expressions which are valid for zero order reactions, and let's try to see exactly how these expressions are used. But before seeing exactly how these expressions are used, let's have a look exactly on a few more things. First thing, I'll be plotting a curve between rate of reaction versus concentration of reactant. Rate of reaction versus concentration of reactant. Well, for the zero order reaction, how do I write the rate law? Rate of the reaction is equal to rate constant multiplied by concentration of A raised power 0. So rate of reaction is independent of concentration of reactant. This is valid for the zero order reaction. Number one, the first curve, right? Similarly, my dear people, the second curve, which I would want you guys to remember for the zero order reaction, that's going to be between AT versus T. Right, AT versus T. So AT versus T, it is in the form of Y is equal to minus mx plus C. So the curve is going to be like this. If I talk about the slope of this particular curve, it's equal to minus k. If I talk about the intercept of this particular curve, it is equal to a naught, right? This is one more curve which I would want you guys to remember. Perfect. Now we can plot one more curve for the zero order kinetics. That is going to be equal to, that's going to be between T half. That's going to be between T half and a naught. That is a T half and initial concentration of reactant. Let's try to plot a curve between these two, right? So T half is going to be y. This a naught is going to be x, so 1 by 2k becomes m, y is equal to mx form, so it's going to be a straight line passing through the origin, and its slope is simply going to be 1 divided by 2k. Perfect. If I want to plot a curve between alpha and a naught for the zero order reactions, what is going to be the curve, my dear people? Right? Inversely relationship, so it's going to be rectangular, hyperbola like this. These are few curves which are basically valid for the zero order reactions. That's all you need to remember, right? Is it perfectly clear, guys? Let me know in the chat still now. Then only I can do some questions. Let me quickly know in the chats if it is super clear to everyone first. Right? Let me know fast, people. Perfect. Perfect, guys. So just give me a second. All right. So let's try to solve the questions. But before solving the questions, let's have a look on the units of the rate constant, my dear people. So these are the general units of the rate constant, where n stands for the order of the reaction. Since right now we are talking about the zero order reaction, so n value has to be 0. If the value of n is 0, so the units of rate constant are going to be moles liter inverse second inverse and atm second inverse, right? Okay. These are basically going to be the units of the rate constant for the zero order reactions. Perfect. And I would want you guys to remember these reactions as well. These are the examples of the zero order reactions, starting with the photochemical reaction between H2 and Cl2, right? In presence of H nu. Then you have got decomposition of NH3 over, decomposition of Hi over gold surface. Then you have got decomposition of NH3 over molybdenum. These are the common examples of the zero order reactions. These are something which you need to remember, that's it, right? So let's try to solve the questions based on the concepts which we have discussed till now. Have a look. The question says that we have got the reaction, for example, A gives B, right? Let's say at time t is equal to 0, the initial concentration of reactant is A naught, this is going to be 0, right? As per the question, a zero order reaction is 20% completed in 10 minutes. 20% completed in 10 minutes. So after 10 minutes, 20% of the reaction got completed. That means 80% of the reactant will be still left in the container. So 0.8 A naught is going to be the concentration of reactant left in the container after time t is equal to 10 minutes, right? What do I need to calculate exactly? I need to calculate at what time will be the 80% of reaction completed. At what time 80% of the reaction would have got converted into the product. And if 80% of the reactant has got converted into the product, I must say 20% of the reactant will be still left in the container, right? So basically I got two conditions. This is condition number 1 and this is condition number 2. Now I'll be using the integrated rate equation, my dear people, right? As far as your integrated rate equation for zero order kinetics is concerned, you know, AT is equal to A naught minus KT. Let me use the first condition. The first condition says AT is equal to 0.8 A naught is equal to A naught minus K. T value in the first condition is 10 minutes. So from here, you can calculate the value of K, which comes out to be 0.2 A naught divided by 10. This is the value of K, right? And its units, few minutes back only you saw, it's going to be moles liter inverse, and over here it's going to be minute inverse, right? Because the time is given in minutes. Perfect. Now we will have a look exactly. Since K value you got, now you'll be using the same integrated rate equation, right? But you'll be using the second condition. As far as your second condition is concerned, AT value in the second condition is 0.2 A naught is equal to A naught minus K. K value already you got, that is 0.2 A naught divided by 10 multiplied by T. And this is the value of T which I need to calculate basically. So A naught gets cancelled everywhere. So you get 0.2 is equal to 1 minus 0.2 divided by 10 multiplied by T. So by solving this equation, you can calculate the value of T. And T value will come out to be simply 40 minutes. T value will come out to be 40 minutes exactly. So the question, as per the question is concerned, I'll say 80% of the reaction will get completed exactly in 40 minutes. That's something which I was supposed to calculate as far as the question is concerned, right? Yes, simple and basic. So let me move on to one more question. This is one more question, my dear people, and say exactly how do I solve these sort of questions. Half-life for a zero order reaction is 1 hour. Okay, so as per the question is concerned, half-life is given as 1 hour, right? So you can calculate the rate constant. K is equal to A naught divided by 2K. Just a second, guys. If I talk about T half is equal to A naught divided by 2K. This is something which you guys must be knowing now, right? For the zero order reactions, few minutes back only we saw this. So first thing, I'll be calculating the rate constant of the reaction over here. It's going to be A naught divided by 2 times the T half. Well, the initial concentration A naught of the reactant is given to me as 2 molar divided by 2 multiplied by T half is given to me as 1, right? So the value comes out to be 1 mole liter inverse R inverse. This is going to be the rate constant which I got over here. Well, after getting the rate constant, what am I supposed to calculate? How much time does it take for the concentration to reduce from 0.5 molar to 0.25 molar? For example, the reaction is like this, right? Let's say at time T1, the concentration of reactant is 0.5 molar. At time T2, the concentration of reactant is 0.25 molar. So I need to calculate basically what is going to be the time for the concentration of reactant to reduce from 0.5 to 0.25, right? Let me call this directly as A naught value now. Let me call this as AT value now. So I'll be using again the integrated rate equation. My AT over here is 0.25 is equal to A naught is 0.5 minus K. K value already we have got, that's 1. And over here you can calculate T. So from here you'll be calculating the value of T, that too in hours. That's something which I was supposed to calculate. So basically this T you were supposed to calculate, right? So this is the time in which the concentration of reactant is being reduced from 0.5 to 0.25 molar, right? That's all. Perfect. Perfect, my dear people. Simple. And the final answer of the equation is coming out to be 0.25 hours. This is one of the simplest ways by means of which you can solve this sort of equation. Yeah? This is one more question, my dear people, on your screen, right? Let's see exactly how this sort of equation is to be solved. First thing, for this particular equation, let's write the differential form. It's going to be minus 1 upon x d of a divided by dt, which is going to be plus 1 upon y. It's going to be d of b divided by dt, right? Let me call this as equation number 1. Let me call this as equation number 1, right? Now people, as far as this particular equation is concerned, as far as this given data is concerned, I can write it as like this: log of minus dA divided by dt is equal to, it's going to be log of plus dB divided by dt plus, instead of 0.3 I'll be writing log of 2. Doesn't make a difference, right? Now we will have a look. It's going to be log of minus times d of a divided by dt is equal to log of m plus n. It's going to be log of m into n, right? So it's going to be 2 multiplied by d of b divided by dt. If I take anti-log on both the sides, it's going to be minus d of a divided by dt is equal to 2 times d of b divided by dt. If I take 2 in the denominator over here, it's going to be minus 1 by 2, change in the concentration of a divided by dt, which is going to be plus times d of b divided by dt. So my dear people, if you compare the two equations, this one and this one, so you'll be exactly getting the value of x over here as 2, the value of x over here we got as 2, and the value of y, which you can see over here, that is exactly equal to the 1. So x value is 2, y value is 1. This is something I was supposed to calculate. I'm sure it's clear to everyone, right? Perfect, guys. Is it clear to everyone? Let me know in the chats. Guys, I think I'll end here only because my throat is a little aching, right? I'll come up with the rest of this chapter in the tomorrow session, right? Okay? Perfect. So in the tomorrow session, we'll continue from the first order kinetics, right? Yes, you'll be getting the PDF of this particular session. Right, in the Telegram group, absolutely. All right. So I'll see you guys tomorrow, okay? Take care. Bye-bye.